start talking about this though, I'd like to give you a little overview of the research in my lab. That's a picture of the group. Many of those students have already graduated, many of them are master's students. But it's the most recent group photo that we have, so I'll put that up here. Generally, we are working in signal processing for wireless communications, and these are a few of the specific projects that we have. So there's two ways to explain what we are doing. One way is to tell you the project that we are doing, and the second is to tell you the specific research topics or problems that we are looking at. This is a list of projects, but it's a little more, a little easier to see what we're doing through the list of topics. We work in basically 4 areas. The first is, 5 areas, and the 5th area is going to be called miscellaneous topics, which is everything else but the 4 areas. The first area is multiple antenna communications. This was the topic of my PhD thesis, and I graduated in 2006, but I still feel like I graduated only yesterday. So I still feel very much like a graduate student. This was the topic of my PhD thesis, and we've continued to work more or less in that area for some of the work that we've been exploring. The work that I'm going to talk about today is the design of training sequences for reciprocal multiple antenna systems. The keyword there is reciprocal, and I'll explain more about that in the rest of the talk. The other topics are data fusion in sensor networks, algorithms for achieving interference alignment, analysis of the generalized degrees of freedom in MIMO interference, multi-user interference channels. The second topic is cognitive radio. We've looked at spectrum sensing, and specifically within spectrum sensing, we've looked at error exponents for signal detection for decentralized spectrum sensing in the presence of fading. We've also looked at group testing based approaches to spectrum sensing. We've looked at footprint identification. So in a cognitive radio setup, you want to figure out where the so-called primary transmitters, the spectrum and the geographic areas that are occupied by so-called primary transmitters. So you can avoid those areas when you're transmitting as a secondary transmitter. So one of the things you need to do is to be able to identify the transmitter footprints using, say, a small number of measurements. And so that's primary communication footprint identification. We've also looked at some information theoretic limits of cognitive radio, where we've used the cognitive radio channel model proposed by Natasha Dagoy and others. And we've looked at the same model under a secure communications setup, where you want to make sure that maybe the cognitive receiver is unable to decode the message of the primary transmitter, etc. The third topic is that of energy harvesting sensors. We basically have pursued 2 lines of inquiry here. The first line is looking at 2-stage algorithms for power management. Both the works have to do with power management. So that is to figure out at what power level and using what modulation coding scheme will an energy harvesting sensor communicate. Okay, if you have not heard of the area, an energy harvesting sensor is basically a sensor that has to use energy harvested from the environment for its communications. And the main constraint that comes up here is that at any point in time, the cumulative energy consumed or utilized by the sensor cannot exceed the cumulative energy harvested by it. So that's a kind of a cumulative energy constraint, which is different from typical average power constraints in communication system design. So in the dual stage algorithm work, what we've done is to look at the fact that the energy harvesting process is usually a very slowly varying process. So as far as channel variations are concerned, the channel variations are very fast in relation to the harvesting process. So so as far as the channel variations are concerned, you can think of the energy harvesting process as a constant energy harvesting process, where you're harvesting energy at a constant rate. And then you can have an outer loop of optimization where you're handling the variations in the energy harvesting rate itself. So that is the dual stage algorithm work. The other work we've looked at is to look at an energy harvesting sensor that uses automatic retransmission requests for transmission. There the question we've asked is at what power level should the sensor node attempt every packet? Rather, at what power level should a sensor transmit every attempt of a packet in order to maximize some notion of a long-term reward. So basically there's a trade-off between using energy to ensure successful delivery of the current packet versus saving energy for delivery of future packets. So that's the trade-off. The next area is more signal processing oriented. It is sparse Bayesian learning. So in the compressive sensing literature, where you're trying to recover a sparse signal from a small number of random measurements, there's basically been two tracks, if you look in the literature, that's been taken. One is that of compressive sensing or compressed sensing itself, and the other is that of sparse Bayesian learning. In sparse Bayesian learning, you have what is called a sparsity promoting prior on the sparse vector, and you look at Bayesian methods to for signal recovery. And typical algorithms are based on things like expectation maximization. And we've looked at two things. One is they're both related. So basically, we've started out by looking at the problem of OFDM channel estimation, and we know that the OFDM channel is sparse in the time domain. And so we've tried to exploit this time domain sparsity to use sparse recovery algorithms for channel estimation and joint channel estimation and data detection. That led to also the question of, are we doing as well as we could possibly be doing? And so for that, we derived a set of Kramer-Rao type bounds for compressible signals. Compressible signals, there is a mathematical definition for compressible signals. But for such types of signals, we've come up with Kramer-Rao type bounds on signal recovery. Then, of course, there's this unclassifiable set of topics that we've worked on, which include source coding for noisy channels, signal detection limits under uncertainty, which is related to the SNR wall proposed by Anand Sahai, and selection problems using decision theory, so Markov decision theory. So this is the outline of the rest of the talk. I will sort of give you the background under which we approached when we started out working on this problem, and then I'll give you some of the results we obtained for reverse channel training with the assumption of perfect channel state information at one of the two nodes. Here it's called the receiver, and then I'll extend that to imperfect channel state information at both nodes. So, two fundamental quantities of interest in any communication system are the reliability and throughput, and the diversity multiplexing gain trade-off basically captures the trade-off between the two. You lose some, you gain the other. If you lose on one, you can gain on the other, and this trade-off is captured by the DMT or diversity multiplexing gain trade-off. One other aspect is that the wireless channel is fading, and due to this, there is a severe loss of reliability and throughput compared to an additive white Gaussian noise channel. And in order to improve the reliability, what you want to do is to learn the channel state at the transmitter or the receiver or both. Actually, typically you start out by learning the channel state at the receiver, and then you would like to learn it also at the transmitter, and when both have channel state information, that's when you can get the best performance possible out of a time varying wireless fading channel. So in order to learn the channel state information at either the transmitter or the receiver, you need to send a training signal from one node to the other, and possibly either on a feedback link. In order to learn the channel state at the transmitter, you could either use reverse training or you could use quantized feedback of the channel state. So for a moment, let's talk about what are the implications of training. There are actually two implications. One of them is obvious. The first one is basically that if you train, then you have channel estimation errors, because there is AWGN that you cannot get rid of. And so there is estimation error, and that can lead to outage of packets. Because based on your estimate of the channel, suppose you pick the transmit power level for the packet, then at that power level, if you underestimated the channel state, then your packet will not go through. So you could have a packet outage. The other implication of training, which is a little less looked at in the literature, is that of time. Basically, it takes time to train the channel. So if you're transmitting at a particular power level, you may want to send some L number of training symbols, and that training duration overhead could lead to a loss of throughput, because you have to train every time the channel changes. So the question that we are asking in this work is what is the effect of imperfect channel state information on the diversity multiplexing gain trade-off performance. So this is the model. It's a very simple model that we've considered. It's very standard also. About this model, I just want to say one or two things. One is that we've considered a single input, multiple output model where there is one antenna at the transmitter or node A, and there are antennas at node B. We have extensions of this to the MIMO case as well, but I won't talk about that here because of just to make the discussion a little bit simpler. The second thing is we are looking at a quasi-static channel model where the channel stays fixed for the coherence time of the channel, which is denoted L sub C symbols here. And it changes in an IID fashion from one coherence time to the next. The third important point I want to make about this model, which is in fact the most relevant point to this discussion, is that of reciprocity. So you notice that the forward channel from node A to node B is denoted by this vector H, and the reverse channel is denoted by the vector H Hermitian. So it's exactly the same channel going either way. So that's one of the assumptions in our work. We'll be considering two different cases. One case where there is Genie provides perfect channel state information to node B, and the other case where the channel state information at node B has also has to be estimated using some training. Yeah, please feel free to stop me at any time if you have questions. Go ahead.
The channel is called single input to R.
Yes.
The reverse channel.
So
the gain is
Why Hermitian? Why
yeah.
conjugation?
So the Hermitian just, is that your question? Yeah. So that just makes some of the maths that follows a little simpler to write. But if you want to be accurate, you want to write transpose, right? H transpose. But if you just take the complex conjugate of what you receive at node A, you can represent the channel as H Hermitian instead. So what happens is that the math of what I have to say becomes easier if I write the reverse channel as H Hermitian. That's all. So what we are interested in is the probability of error versus data rate kind of trade-off. But it's been long accepted that at high SNR you can approximate the probability of error with the outage probability and the data rate with the degrees of freedom. So this is the proxy that we will use in this work. So we'll look at the diversity multiplexing gain trade-off performance, which has to do with the outage probability versus the degrees of freedom. So mathematically, the multiplexing gain is defined as the scaling of the target data rate, which is denoted RP bar, to the log of the transmit power, or the transmit power in the dB scale, as the transmit power goes to infinity. So that limit is denoted by GM, and that's the multiplexing gain. And the outage probability is the slope of the negative slope of the outage probability versus SNR in the log-log scale. And so we are interested in exploring the trade-off between D and GM. Outage probability itself is defined as the probability that the capacity of the channel is below RP bar. And so what you end up doing often is to find upper bounds or outer bounds on the outage probability, and that leads to an achievable diversity multiplexing gain trade-off. One small notational thing is that we are going to use this FP bar dot equals notation. So dot equals P bar for K is used to mean that the log of FP bar divided by log P bar, as P bar gets large, becomes equal to K. So I'll start with a very simple motivating example of which will motivate the kind of things gains we are looking for in this work. Let's consider a single input, single output Rayleigh fading channel. So there's just only one scalar channel between the transmitter and receiver, and assume that the receiver has channel state information and the transmitter has no CSI. Let's say the data power constraint at the transmitter is P bar, and the channel is Rayleigh fading, so H squared is exponentially distributed. For this channel, the outage probability is very simple. It's the probability that log of 1 plus H squared P bar, this is the data rate achievable by the channel. Probability that is smaller than your target data rate, which is GM log P bar if you're trying to achieve a multiplexing gain of GM. And it's very easy to show, since h squared is exponentially distributed, that this quantity is dot equal to 1 over p bar power 1 minus gm. And so the diversity order that's achievable by in a Saiso-Rayleigh channel with perfect CSIR and no CSIT is V of gm, which is 1 minus gm. Now the question is, can you do better than this? So to answer that, let's consider this power control here, which is something I've essentially pulled out of a hat, but you will see later that there is a reason why it works. But basically what we'll do is we'll look at the channel gain, and if that is larger than 1 over p bar, we will use power p bar to transmit. And if it's smaller than 1 over p bar, we will, instead of using p bar, let's use p bar square to transmit. So we try to use more power when the channel is in a bad state, and just p bar power when the channel is in a good state, where good and bad is defined as 1 over p bar, whether the channel gain square exceeds or is smaller than 1 over p bar. This, plus there's a factor beta, which is a normalization factor. It is chosen such that the expected value of this transmit power is equal to p bar. That's our power constraint. This requires 1 bit of feedback from the receiver to the transmitter, because the transmitter now needs to know whether h squared is greater than 1 over p bar or it's smaller than 1 over p bar in order to choose the appropriate power level. So if you allow 1 bit of feedback from the receiver to the transmitter, you can implement this power control. And if you work out similar to the previous slide, what the diversity order that's achievable by this power control is, it's easy to show, it's very easy to show that it is 2 minus gm. Okay, the interesting thing is, instead of 1 minus gm, you're now getting 2 minus gm. And even when gm is equal to 0, that is, you're transmitting at a constant rate, you can double the diversity order. At higher values of gm, for example, gm close to 1, you can do a lot more than doubling. Right? So you can tremendously improve the diversity order if you have just 1 bit of feedback from the receiver to the transmitter. So this is the first kind of key take-home message that I'd like to convey, that even imperfect CSI at the transmitter can improve the diversity multiplexing gain trade-off, and improve by a large margin. So this power control here, it actually captures 2 or 3 of the very essential features of good power control schemes. One is that it's transmitting, remember that here we have a target data rate, and if the data rate that is achievable by the channel is smaller than this target data rate, you're going to go into an outage. So for bad channel states, it's good to use higher power levels, and vice versa. And so this is trying to transmit at a higher power level for bad channels. But another very important thing about this power control scheme here is the threshold of 1 over p bar. So that threshold at which you're going to decide that the channel is in a bad state is something that's going to 0. And we'll see that all the power control schemes that we propose in this work is going to have this quality to it. So this kind of observations are not new. There are several works in the literature that have made these kinds of observations with either from a diversity multiplexing gain trade-off perspective, or from a data rate, or a simple outage probability, or with rate control, power control, etc. So there's quite a bit of literature in this area. The work that is closest to the kind of work that I'm going to talk about is the work by Agarwal and Sabharwal in 2010 and Steger and Sabharwal in 2008. So those are the kind, in flavor, the work that I'm going to talk about is closest to these works. Okay, so as I showed you with the Saiso channel example, acquiring channel state information, even imperfect channel state information at the transmitter is very helpful in improving the diversity multiplexing gain trade-off. And so the question is, how do you acquire channel state information at the transmitter? Basically, there's 2 approaches that have been explored in the literature. One is through quantized channel state information feedback. This was also the topic of my PhD thesis. So obviously I didn't want to do that when I started working at IISc. So the other alternative is to feedback the channel state using training in the reverse link. So that is what you would call an analog feedback. So this is useful in a time division duplex system where the forward link transmission happens and then the reverse link transmission happens, so that they happen one after the other and immediately after the other, so that you can assume the channel doesn't change between the forward transmission and the reverse transmission. These two feedback schemes are actually quite fundamentally different. For example, in Quantized Csi Feedback, you can imagine that except for what you would call the overload regions, for many of the regions where you quantize the channel state, you have a bounded uncertainty in the channel state. Whereas if you feedback using analog feedback or you train in the reverse link, noise could throw you anywhere. So the uncertainty interval is unbounded. In this work, we will focus, as I said, on reverse channel training. So this is the model. So there is the channel from between the transmitter and receiver is H, and you have training, which will denote X, B, tau. Tau or T stands for training in the reverse link. So first of all, if this training was done at infinite power, then you could acquire perfect channel state information at both the receiver and transmitter. A pertinent question to ask is, what is the diversity multiplexing gain trade-off of such a channel? And so the answer is very simple, which is that, so it's written a little more complicated way here, but the answer is very simple. You can achieve an infinite diversity order if you do a simple channel inversion power control. So this P of sigma written here, what it's doing is it's looking at the target data rate and the current channel state, which is where what matters is the singular value of the channel. So say the channel H is written as sigma times B. B is a beamforming vector in the direction of the channel. Sigma is just the singular value. So if you invert that singular value and use 1 over sigma square times an appropriate scaling to ensure that your target data rate, data sent at your target data rate will be successfully received, that is sufficient to ensure that you get an infinite diversity order. That is, for any channel state, your data will always be received successfully at your target data rate. So this is true if, for example, for a Rayleigh fading channel, if you have a single antenna at the receiver and a single antenna at the transmitter, this is not possible because 1 over sigma square is, in expectation, is unbounded. So, but as long as you have at least 2 antennas at the receiver, 1 over sigma squared is a chi-squared with 4 degrees of freedom, and that has a bounded mean. So you can always do this as long as you have at least 2 receive antennas. And you can achieve an infinite diversity order. So channel inversion power control is good because it achieves infinite diversity order if you have perfect CSI at the transmitter. So when you don't have perfect channel state information at the transmitter, things get a little more complicated because you need to do two things in addition. You need to do at least 2 things before you can talk about what the diversity multiplexing gain trade-off is. The first thing is to come up with a way to estimate the channel state information at node A. And then the second is to find a way to map the estimated channel state information to a transmit power level. In other words, perhaps it is simpler to think of it in terms of coming up with an optimum or coming up with a way to map your received reverse channel training signal to the transmit power level for the data signal in the forward direction. So once you come up with such a mapping, you can talk about what is the diversity multiplexing gain trade-off achievable by that mapping. So that is a sort of simpler problem than to try to figure out among all possible mappings what is the best diversity multiplexing gain trade-off that is achievable. So in this work, what we are going to do is to propose a way to estimate channel state information at node A and propose a way to map that estimated channel state information to a power control, and then discuss what its achievable diversity multiplexing gain trade-off is. So some notation, we will use the subscript T for training. So YAT is the received training signal at node A, and YBB is the received data signal at node B when data is transmitted from node A to node B. So XB tau is the reverse training signal, and the forward data signal is XAB. And W is the noise. So in conventionally, if you want to train in the reverse link, you would use what is called orthogonal training, where, for example, you would use the R cross R identity matrix, transmit training signal from the first antenna, then a training signal from the second, third, fourth, up to the rth antenna. So if you use the R cross R identity matrix, you need at least R symbols to train in the reverse link. And if you use the minimum mean squared error channel estimation, so often you will see in this kind of work people using the minimum mean squared error channel estimator for the channel, because it enables what is called a famous theorem called the worst case noise theorem, which says that of all possible noises, the Gaussian noise is the worst in simple terms. It enables the use of that theorem to figure out what the achievable data rate of the channel is. So that's why you often see MMSE estimation being used. And once you've estimated the channel, you can use the estimated channel to set the power level for data transmission. So you use 1 over the estimated channel square as your power level. Yes, please.
I'm sorry, what is R?
What is R?
Yeah, what is the little R?
Yeah. So R here is the number of receive antennas. So we are considering a single input, multiple output system with R antennas at the receiver and 1 antenna at the transmitter. So R here is the number of antennas at node B. So if you want to train in the reverse link, you need to use at least R symbols if you use conventional training. So you send a training signal from the first antenna, second, third, fourth, up to the rth antenna. So as we discussed earlier, inverting the channel gain is the channel power gain is going to achieve infinite diversity order if you had sigma square perfectly known at the transmitter. But now we don't. But nonetheless, let's use the estimated singular value of the channel and invert that. And let's embellish it a little bit by considering C. C is just a normalization constant divided by sigma hat square power 2s, where when you set s equals 1, that's like inverting the channel power gain, estimated channel power gain. And when s equals r, you are doing something a little tricky, but it captures the essential idea, which is to use higher power levels for worst channel states. The reason for using s equal to 1 through r, that particular range, is when you set s equals 1, for this range, it turns out it's possible to ensure by choosing C appropriately that you meet the average power constraint. That is, the expected value of P of sigma hat should be less than or equal to P bar. So that constraint can be met for this range of S. So this is the range that is considered in the literature. So this is conventional. This is a conventional scheme. So this is not our work. This is what was derived in Steger and Sabharwal paper 2008, where they showed that if you do this, the achievable diversity multiplexing gain trade-off is this expression here, which is R times delta minus GM over alpha. So R here is the number of receive antennas, and alpha here is basically the fractional loss due to training overhead. So LC is your coherence time. Out of that LC time, you use R times LB tau. Think of LB tau as 1 if. I mean, you need to train for at least one symbol duration on each of the antennas. So LC minus R times LB tau divided by LC. So that's the fraction of time, fraction of the coherence time of the channel that you have available for sending data. And and delta is just another factor which is equal to 2 if you are using S equals 1. And if you use S equals R, then delta turns out to be R plus 1. So, so that's basically the result derived in that paper. And that's true for GM between 0 and alpha, where again alpha is the fractional loss. In fact, it's the fractional time available for data transmission when you consider, when you account for the training overhead. So all of this discussion is relevant only when the training duration occupies a significant portion of the coherence time of the channel. So for very slowly varying channels where the training duration occupies negligible overhead, this discussion is completely irrelevant. It's a moot point. Okay? It's valid for fast varying channels where you want to train as fast as possible. One other feature or one other aspect of this result is that it assumes that this P of sigma hat is known at the receiver. So this is what is called a geniated receiver. Otherwise, you would have to learn the P of sigma hat at the receiver. But nonetheless, the one observation from this result is that the training overhead reduces the achievable diversity multiplexing gain trade-off. In fact, if the coherence time reduces, or rather if the channel is very fast varying, you cannot achieve a non-zero multiplexing gain if R is actually larger than LC divided by L beta. So, the solution proposed in that paper is to switch off antennas till your R reduces to be below LC minus L beta. So then you can achieve non-zero multiplexing. So now I'm finally, with that background, able to talk a little bit about what we have been able to do with this model. So what we do, what we do is we start with proposing a training sequence. The training sequence we propose here is with is very simple, which is to use. So remember that we are assuming that the receiver, that is node B, has perfect channel state information. Okay, and later I'll show extensions of this to the case where node B does not have perfect channel state information. But for a moment, if you assume that there has been a forward training, a round of forward training, which has been which is at very high power, so that node B has perfect channel state information. Since node B has perfect channel state information, you can use the normalized channel, which is denoted V, so that is H over norm of H, and use that to train in the reverse loop. And this, if you use V as a beamforming vector for transmitting your training signal, if you multiply that with the channel, you will be left with just sigma plus noise, and of course sigma is a real valued quantity, real valued positive quantity. So from the received signal you can extract the real part because the imaginary part contains no useful signal component, and then you can normalize by the training power, and that will give you an unbiased estimator of the channel singular value. So this is how we estimate the channel singular value at node A. And this training signal, it requires just one training signal as compared to the conventional orthogonal training, which requires at least R training symbols. I suppose the key observation here is that what you want to estimate at the transmitter in a single output, multiple output system is just the singular value of the channel and not the entire channel itself. And what conventional orthogonal training is doing is it's allowing you to estimate the entire channel vector, and from that you compute the singular value, and from that you compute the power level. But what we are doing is not to estimate, we are avoiding, if you use V as your reverse training signal, you cannot possibly get what H is at the transmitter. You can only estimate the singular value, but that's all the transmitter cares about.
Don't you get a better estimate when you send more training sequences?
So
Are you losing a throughput or something like that? Is that why you stop training?
The reason why we want to train as fast as possible is because the coherence time is fixed, and it's, let's say, a small number. So suppose you have, say, 5 antennas and the coherence time is only 40 symbols. And if you take 5 symbols to train, then 5 out of 40 symbols get lost in training itself. And so what we're trying to say is you can achieve a better diversity multiplexing gain trade-off if instead of using 5 symbols to train, you just use 1 symbol to train, but you exploit the beamforming vector which is already available. So this is like transmitting a training signal simultaneously from all the antennas, but using the beamforming vector as a kind of gain applied to each antenna. So as I said earlier, in addition to an estimation scheme, you also have to propose a data power control scheme, and this is the data power control scheme that we propose. So recall that if you had perfect CSI at the transmitter, you want to use channel inversion. That's that formula, the first formula in this slide. What we consider here, so that is channel inversion, and what we consider here is what we call a modified truncated channel inversion. This is a truncated channel inversion because you are truncating the channel inversion to some threshold which is 1 over square root of p bar. So you use channel inversion power if sigma hat squared is greater than 1 over p bar, but you don't use channel inversion if it's smaller than that. And normally truncated channel inversion would ask you to transmit at 0 power if sigma hat squared is less than 1 over square root of p bar. But this training scheme is better because it's trying to account for the fact that if your estimated singular value is small, that may just be because of noise. It may not be that the channel state itself is bad. So even though you get a sigma hat that is smaller than 1 over p bar, it is saying just don't try to invert the channel, but transmit at some power, say p bar power L, and L is a parameter that we can optimize. And if the singular value sigma hat is greater than 1 over p bar, then you use the channel inversion power control. Basically, the tricky part here is for the given channel estimation procedure and the given power control scheme, we want to carefully work out what the outage probability is and work out the outage probability to multiplexing gain trade-off performance. And so partly these are motivated, these kinds of choices are partly motivated by achieving a better DMT performance, and partly by being able to carefully account for the different sources of outage and account and figure out their behavior as the transmit power is going to infinity. So this is analyzable and it gives good performance. And notice that this has the feature I mentioned earlier, which is that the threshold to which you want to compare the estimated singular value of the channel 2 is compared to 1 over square root of p bar, so that threshold is going to 0 as p bar gets large. So you want to basically invert every channel state and if you have infinite power at your disposal. The other thing is you should be able to satisfy an average power constraint on the data. And so the first little exercise we had to do was to show that if you use s equal to 1 through r, any value of s between 1 and r, you can satisfy an average power constraint. And that is a bit of math, but it can be shown that an average power constraint can be satisfied. And not only that, this kp bar, which is a normalization constant, it varies as p bar to the 1 minus gm over alpha as p bar is large. Once again, alpha is the fractional time spent transmitting data, so it's LC minus, that's the coherent time, minus the training duration divided by S. Yes, please.
So S is the number of transmitting antenna, right? Which is node A.
No. So S is just, so in this equation here, S and L are actually two factors that I've put in just to allow me to optimize things a little bit. So these are free parameters here.
Oh, S is the free.
So just to go back here a few slides. So in Steger and Sabawal's work, they considered this kind of a power control, where if you have, so sigma hat is an estimate of the channel norm, okay? And the power level value they use for transmitting the data is some constant divided by sigma hat power 2s. And S is just a parameter that is used to improve the diversity multiplexing gain trade-off.
So, okay, so only the result for S equals to 1 or R are known. How about
it varies continuously between them. So for values in between, you can also work out what the diversity multiplexing gain trade-off is. But what happens is that if you look at the result, you see that the diversity multiplexing gain trade-off is R times delta minus GM over alpha, and delta is 2 for S equals 1, and delta is R plus 1 when S equals R. So the best DMT you will get is when delta equals R, when S equals R. So S equals R is basically the way you want to go. And S equals 1 corresponds to the standard channel inversion power control. Yeah, so if you look at this power control here, if I say S equals R, what it means is that basically when the channel gain is very, very small, I'm going to take 1 over sigma hat power 2R. That's the power level at which I'm going to try to transmit the data, which could be a very large number. So if you have a peak power constraint, maybe you cannot implement 1 over sigma hat power 2R. But maybe 1 over sigma hat power 2 is better. So, but if you don't have such constraints, then using S equals R is always better. Okay, so now we have chosen a reverse channel training scheme. We have chosen a data power control scheme. And then you can ask what is its diversity multiplexing gain trade-off. And this is the result that we were able to obtain. That the diversity multiplexing gain trade-off has a form which is very similar to, this is an achievable diversity multiplexing gain trade-off. And it's a form which is very similar to the result in Steger and Sabova's paper in 2008, which is that it is R times delta minus GM over alpha, where alpha is now LC minus LB training, that's the training duration, divided by LC. And again, delta equals 2 when S equals 1, and delta equals R plus 1 when S equal to R. So in flavor, the result is very similar. It also assumes a geniated receiver where the power control, that is P of sigma hat, is assumed to be known to the receiver using a gene. So are we better off? So this is the diversity multiplexing gain trade-off of the conventional scheme. And this is the diversity the lower equation is the diversity multiplexing gain trade-off of the proposed scheme. And the difference is highlighted in red. You see that the difference is basically in this training overhead and the way it affects the diversity multiplexing gain trade-off. And in one case you have, in the conventional case, you have R times LB tau, and in the proposed, the scheme that we have explored, you only have LB tau. So once again, this is relevant, or this offers a significant improvement when LC is comparable to LB tau. So basically, if you have training power which is fixed to be equal to P bar, if you use this proposed training scheme, which is basically to beamform in the reverse link, you can achieve, and the proposed power control scheme, which is a modified version of truncated power channel inversion, it significantly improves the diversity multiplexing gain trade-off. And moreover, having a larger number of receive antennas is always better. So this is in contrast with what you would get if you use conventional training. If as R increases, eventually you see that basically if LC minus R LB tau becomes negative, then you cannot achieve any non-zero multiplexing gain. So this is just a schematic plot of the equation you saw in the previous slide, which just shows that for a R equal to 4 antenna case, the y-axis is the diversity order, the x-axis is the multiplexing gain. So this is the diversity multiplexing gain trade-off. The blue curve is the performance, the diversity multiplexing gain performance of the proposed scheme, while the red dashed curve is the diversity multiplexing gain trade-off of the orthogonal scheme. And you see that the orthogonal training scheme is the diversity multiplexing trade-off achievable by the orthogonal scheme is somewhat worse than that of the proposed scheme. And the sort of stepwise drop off there corresponds to switching off antennas one by one. So up until say a multiplexing gain of 0.5, you can use all 4 antennas. From 0.5 to about 0.62, 63, something like that. You can use 3 antennas, then 2 antennas, and then finally 1 antenna. So that's basically the diversity multiplexing gain trade-off. This is a simulation result. It's just plotting the outage probability versus the transmit power for the proposed scheme, which is in red, and the conventional scheme, which is in blue, for constant rate, which is GM equals 0, and GM equals 0.8. And you see once again from the increased slope that the proposed scheme achieves a better diversity order. This is again a plot of the outage probability versus transmit power for the proposed scheme, but for different rates and multiplexing gains. So it just shows, it's just a nice simulation result. It's a simulation result with S equal to R, whereas I think the previous result was with S equal to 1. So far, we assumed that node B, that is the receiver, has perfect channel state information. We assume that there is a geniated receiver, that is the power control used by the transmitter is known to the receiver. And we showed that a diversity order of R times, when S equal to R, R plus 1 minus GM over alpha is achievable if you use constant power training for GM between 0 and alpha. We've also been able to extend this to the case where you have an average power constraint on the reverse channel training as well. So our training signal had a constant power in what I showed you earlier, but you could also consider an extension where the reverse training has an average power constraint on it. And what we are able to show there is for the same range, that is GM between 0 and alpha, you can actually achieve an infinite diversity order. And in other words, you can achieve a performance similar to an AWG channel if you use power controlled reverse channel training. But the next, so this is all under the setup of perfect CSIR and a gene-aided receiver. So the next question is, what can you say about the diversity multiplexing gate trade-off if the CSI is actually estimated at the receiver and you don't have a gene-aided gene-aided receiver which knows the power control used by the receiver. To analyze this setup, I'm just going to give you the main result in the interest of time. But we can take questions, or if you're more interested in this, we can discuss it offline later. But basically, what you need to do in this case is to look at a 4-phase protocol where you consider forward training, where node A transmits a training signal to node B. Node B estimates the channel state H. Then you have to consider reverse training, which is similar to what I showed you earlier, where you use beamforming from node B to transmit the reverse training signal, and you estimate the singular value at node A. Then you use the estimated singular value to come up with the transmit power level for the data, but you need to convey that transmit power level to the receiver. So if the receiver doesn't know at what power level you are transmitting data, it won't know. It won't know at what modulation and coding scheme you are using in some sense. So here we are talking about achievable data rates. So it's not like you're really changing the modulation and coding scheme, but nonetheless, the transmit power level used by the transmitter does need to be available at the receiver. So you train for the second round from node A to node B. This time you send the power control itself, that is the P of sigma hat, to the receiver, the power control that we use for data transmission. And using this, the node B estimates the channel H times the power control. So it estimates the composite channel at the receiver. And then you have a data transmission phase where node A transmits power control to data to node B. Analyzing the DMT performance of this protocol involves basically very careful bookkeeping of the various sources of outage probability and accounting for exactly how they vary with the transmit power level. So it's a lot of math, but the end result is that the achievable diversity multiplexing gain trade-off has a form which is very similar to what I showed you earlier. This is the result for S equal to 1. For S equal to R, you have a similar result as well. But when S equals 1, you get diversity multiplexing gain trade-off of R times 2 minus GM over alpha, where alpha now is slightly different. It includes the training overhead from all 3 phases of training. So it's LC minus the sum of the training durations in all 3 directions, all 3 phases divided by LC. So even without perfect CSIR and even without gene-aided receivers, a gene-aided receiver, you can achieve a better DMT performance compared to no CSI at the transmitter by using reverse channel training. That's the key take-home message from this. So that brings me to my last slide, which is that even imperfect channel state information at the transmitter helps to achieve better diversity multiplexing gain trade-off. And the key ingredients to achieving this better multiplexing gain trade-off were, one is to exploit channel state information at the receiver in designing the reverse channel training sequence. Normally when you think about training, what you think of is that you want the training sequence itself to be known to the recipient of the training. If you don't even know what the training signal was, it's hard to estimate the channel. But for certain types of channels and for example data transmission, you actually don't need to estimate the whole channel. So in such scenarios, you can actually use beamforming, where if you use beamforming, for example, V is not known to node A. V is the channel singular vector, it's not known to node A, but still you can use V as a training signal because you don't need to or you don't want to estimate V at node A. You just want to estimate the singular value of the channel at node A. So exploiting channel state information at the receiver helps. And you want to use, you also want to convey only the channel state information that is required for data transmission to node A. You don't want to convey the entire channel state information. and you want to use better power control strategies at the transmitter. And with imperfect channel state information at the receiver, you want to use a third round of training to convey the transmit power level used by the transmitter to the receiver. And this can lead to reduction in the training overhead, better channel estimation, and most importantly to this talk, an improvement in the diversity multiplexing gain trade-off. So there are other things that we have studied, but I mean with this model that we've studied, but I have not talked about today, which is extensions to the multiple input, multiple output. That's the MIMO channel, and with spatial multiplexing at the transmitter, and we also have multi-user extensions, etc., which is there in several of these publications. So that concludes my talk. Thank you again for coming. Appreciate your questions and time.
More questions?
Yeah, I have a quick question. So how exactly does a degree of freedom relate to the throughput? I know you use some definition from previous study.
Yeah. So we are using just this. So RP bar here is your target data rate. So basically the idea here is that the transmitter is going to attempt to transmit at a rate RP bar. If the capacity of the channel is smaller than RP bar, then you will not be able to successfully communicate at a rate RP bar, and you say that you've gone into outage. So RP bar is really your throughput here, but you won't achieve RP bar with probability 1. Okay? And so that's how it's related to the throughput.
So how sensitive this entire thing is for the forward and backward channels being equal? Have you tried?
See, to some extent, the extension that we have here to the three-way training can capture this lack of reciprocity. In other words, you consider the lack of reciprocity as an additional noise which is introduced at one of the nodes. So to that extent, it is not sensitive, right? Because what we've shown is you can achieve basically the same diversity multiplexing gain trade-off with imperfect CSI at both nodes as with without that is even if you train in both directions compared to if you are not if you're assuming a perfect CSI at one end. But there are different models for this. So okay, I suppose no. A more precise answer to your question is that I don't know. The reason is because in this model, as you train, we are taking P bar to infinity here. And so as P bar goes to infinity, essentially your estimation error is going to 0. All you're trying to do is to make sure that your target data rate is such that is scaled at in such a way with the transmit power, such that your outage probability can beat the loss in throughput caused because of estimation errors. So basically your estimation error is getting smaller as P bar gets large. Whereas if there's a loss of reciprocity, the channels are actually not reciprocal, that source of noise may not actually go to 0 as P bar goes to infinity. So I don't think that this analysis actually captures that effect. So yeah, we haven't really looked at that.
Okay, thank you very much again.
Thank you.